Have you ever wondered how our solar system came into existence? The popular theory points to the gravitational collapse of an interstellar cloud, leading to the formation of a solar nebula, a giant spinning disk of gas and dust. Now picture this. As this cloud collapses under its own gravity and starts rotating, larger objects begin to form due to collisions and coalescence. Imagine countless particles of dust and gas, swirling and crashing into each other, gradually growing in size. These collisions and the resulting coalescence led to the creation of larger objects. It's a process akin to rolling a small snowball down a hill, gathering more snow along the way, until it becomes a massive snow boulder at the bottom. In the same way, this cosmic process led to the formation of celestial bodies, such as planets and moons, each unique in its size, composition, and distance from the sun. It's a fascinating journey from a nebulous cloud of dust and gas to a structured, orderly solar system. So, our solar system's birth was a result of a cosmic ballet of dust, gas, and gravity. Now, you may be thinking, why are the inner planets rocky and the outer planets gaseous? Well, the answer lies in their distance from the sun and the conditions that prevailed during their formation. You see, our solar system was born from a spinning cloud of gas and dust, called the solar nebula. As this cloud collapsed under its own gravity, it began to spin faster and faster, with the center of the spin forming the sun. The remaining material started to collide and coalesce, forming larger and larger bodies. But here's the interesting part. The distance from the sun played a critical role in determining what these bodies were made of. Close to the sun, where it was hot, volatile substances like water, methane, and ammonia couldn't condense. They remained as gases and were blown away by the solar wind. So the planets that formed here, like Mercury, Venus, Earth, and Mars, are primarily made of rock and metal. Farther out from the sun, where it was cooler, these volatile substances could condense and form ices. This is why the outer planets like Jupiter, Saturn, Uranus, and Neptune acquired more mass. They had access to more building materials in the form of ices, which increased their size and allowed them to capture large amounts of gas from the solar nebula, giving them their thick, gaseous atmospheres. But it's not just about size or composition. The distance from the sun also influenced the planet's temperatures, atmospheres, magnetic fields, and even the potential for life. For instance, our Earth is in the Goldilocks zone, not too hot and not too cold, just right for liquid water to exist and life to flourish. So the next time you gaze up at the night sky and marvel at the twinkling planets, remember, their location in our solar system is not random. It's a direct result of the conditions that prevailed when they were formed. As it turns out, where a planet is born in the solar system determines what it's made of. But not all solar systems are like ours. Some have posed significant challenges to our understanding. The solar nebula model, for instance, has faced its fair share of scrutiny. Discoveries of other solar systems have thrown a curveball to this model. Some of these systems house giant planets located surprisingly close to their stars, a stark contrast to our own solar system's layout. Then there's Jupiter. Our largest planetary neighbor has always been a source of fascination, and its atmosphere is no exception. Findings about its atmosphere have been unexpected and at times contradictory to the predictions of the solar nebula model. For instance, the abundance of certain elements in Jupiter's atmosphere has left scientists scratching their heads, questioning the model's validity. Despite these challenges, the solar nebula model still holds its ground. It's constantly being refined and updated to incorporate these new discoveries. It's a testament to the dynamic nature of science and how our understanding of the universe evolves with each new finding. These discoveries remind us that the universe is full of surprises. So, where do we stand today in our understanding of solar system formation? Despite some challenges, the solar nebula model remains a key theory, largely due to compelling observational evidence. We see disks around young stars that mirror the early stages of our own solar system, providing a glimpse into the past. Not only that, we have also witnessed the rapid formation of planets, reinforcing this model. One of the crucial processes in this model is accretion. It sees the creation of planetesimals, tiny solid objects that are believed to exist in protoplanetary disks. These planetesimals aren't just bystanders, they're active participants in the formation of the solar system. They collide, coalesce, and grow, eventually forming larger objects, our planets. The energy resulting from these impacts can lead to vaporization and melting, spawning bodies as large as the Moon or Mars. This is our current understanding, but the universe is a vast and mysterious place. With every new telescope and space probe, we unlock more of its secrets. As we continue to explore space, who knows what other fascinating discoveries await us?